Okay, guys, so I want to start us off today with decimal, really. I really want you to know what kind of decimal we have out there. Do you know how many types of decimal we have? Yes?
About a million?
No, okay. We only have three specific types. So we're going to go ahead and start naming each type here so you can actually watch it. The type of decimals that we have here in math anyway. So the first type I want to name is called terminating decimal. Have you heard of that before?
No.
Never heard of terminating decimal?
No.
I think
Well,
I've heard of it.
good. You heard of it. Terminating simply means it stopped. So here's an example. Listen carefully. 1.5. I stopped. I did not go on. So an example is 1.5. Okay? 2.7. 1.6. 0.2. Those are all terminating because notice I stopped after a certain digit and I did not go on. Here's the next one. Next one is called repeating. And just like its name, it will repeat forever and you will definitely notice a pattern. Yes?
Like 1/3?
Very good. So here we go. Here's repeating. 0.3. 3. 3. 3. 3. 3. 3. 3. 3. It goes on and on and on. And it will never stop. And you will definitely notice a pattern. Okay? So I'm just going to write one here. And this is, of course, either we write it that way or we write the bar on top to indicate that it's repeated, right? Or here's another type. Another kind example. 0.23. 23. 23. 23. Notice it's repeating. And you see a pattern? As long as you see a pattern, it's repeating. That's under repeating decimal category. Okay? Here's the third type. And let me just change the color a little bit. Oh. Third type is called a non-repeating and non-terminating decimal. Okay, so notice what it says. So it would never terminate, that means it will go on forever, but it would never repeat, so you basically would never hear me repeating the number again and again. Yes, what kind of number is that?
Pi.
Very good. Pi is a good example of that. Pi, because if you go on 3.14, it goes on forever, and you will never ever see a repeating digit. Is it? That's the main difference, and I purposely use a different color to show you that it's definitely different from the top two. Okay, but I want you to go back here and revisit the first one right here and ask yourself this question: for that terminating decimal, for any terminating decimal, can I take that number and convert it back into a fraction?
Yeah.
Yes, interestingly enough, you can. So how do I convert 1.5 into a fraction? What is 1.5?
1 5 10.
1.50.
A fraction. Can you take 1.5 and convert it back to a
Yes,
fraction?
yes.
Yes. What is it? What is it going to be? How do you convert it? Okay, remember when you learned how to convert decimal into a fraction? How do you convert that 1.5 into a fraction?
1/2.
That's only 0.5. If you say 1/2. How do you say 1.5 in fraction form? Yes.
1.5.
1.5. This is a mixed number, not a fraction yet. What is 1.5? Do we know how to convert it? Let me just show you again, if you don't recall this. But remember, back in the day, when we have 1.5 converted back to a fraction, we look at the last digit here, and we look at the place value of that digit. What place value is that?
10.
A 10. So that means we now drop the decimal, we write 15 over 10, reduced to
1/5.
3/2, which is 1 and 1/2, which is 1.5. This is a mixed number, not a fraction. When I say fraction, I want either improper or proper. You got to understand the difference. Is that clear? So any terminating decimal can be converted back into a fraction, and that's how we do it. Just a rough example of it. What about repeating? Notice you said before, 0.3333 repeated can be converted back to what?
1/3.
1/3. You see that? That's an equivalent. It's the same. So any repeating decimal will be able to convert back to a fraction. So the top two can always be converted back to a fraction, right? If it's repeated, or if it's terminating, you can always count on getting back to a fraction form. Look at the third kind. Can we convert pi to a fraction?
Yeah.
Yes.
Interesting. Who said yes? What's your fraction then?
Oh, that's a good fraction.
3 and 14. 14 out of 100.
But it will never ever end. 3.14 is just a snapshot of pi. It goes on forever. If it never terminates, how do you know what place value is the last digit? Ah, you see that? You have to count on it terminating in order for you to count on, well, in order for you to determine the place value of the last digit. Pi never terminates. Pi never repeats either. So there's no pattern in pi. How do you find a fraction? I know some of your teacher in the past might have said 22 over 7. Right? That's a fraction of pi. But that is only an estimation of pi. That's not pi. That's not how you represent pi. So in that case, pi can never be written as a fraction. So, fraction right here, not possible. So the third type of decimal cannot be written as a fraction. So I want you to keep those three types in your head right now, and we'll start with our number systems. Any questions so far on the three types of decimals? Are we good with those? Okay, good. So now I'm going to jump right into our number systems today. And the first thing I want to show you is a big egg. Okay? This big egg right here contains every number that you have learned since your preschool day. Back in the day, when you first learned, you learned how to count, right? Basic number, 1, 2, 3. You might learn 0, 2, and so on and so on. And then when you go to 5th grade or whatever, or 3rd, 4th grade, you start learning about decimals, fractions, and then when you go a bit higher, you start learning about square roots and stuff like that, right? And integers. Every kind of number that you've learned so far is inside this egg right here, and we call any kind of number that you've learned, we call them real numbers. Okay, so I'm just going to label that. We call real numbers. Any number that you've used so far in your life. Real numbers. Okay, now we start going deeper into this egg to explore this little portion right here, very small. We call that natural number. Okay, and natural number, as it turns out, is basically whole numbers starting from 1 on up. 1, 2, 3, 4, 5, goes on forever. No decimal. See that? So whole numbers, no 0. And then the next layer out, which is a bigger layer, that layer is called whole number. Well, as it turns out, this whole number contains every natural number, right? Plus, it contains 0 in it as well. So what's the main difference between a natural number and a whole number?
0.
Natural doesn't have 0, and whole number has 0, plus everything in natural. So natural is 1, 2, 3, 4, 5, and then whole number is 0, 1, 2, 3, 4, 5. So that's the only thing that's different. Is that hard to not remember? Yes?
Why doesn't natural have 0?
Well, because that's the way we classify numbers. You know, like y is blue, blue, you know? Yeah, that's what you're asking me. I'm sorry. But that's what it is. We just have this set of number and we happen to call it natural. Okay, so next one. And now we come down to our next set of numbers, and this set of numbers, what do you think this next set of number is going to be?
Decimals.
Integers, very good. This next set we have here is called integers. So as you can see, integers contains everything in this. That means it has 0, it has 1, 2, 3, 4, 5, and it's also contained all the negative signs.
Oh,
Notice I said all negative whole numbers. No decimal yet, huh? You've never seen yet. You don't know what decimals yet. Not at this point. And now as we go one layer out, here's the next layer. This next layer outside, the bigger layer. that one. Now we call this
Rational
numbers. Now, as you can see, rational number contains everything inside natural. It contains whole numbers as well. It contains integers, so as you can see, that it covers all the negative, all the positive, whole numbers, right? Plus, I also have plus. It covers terminating decimals, and it also covers repeating decimals. But what's unique about these two that I just covered before? These two can also be converted to what? Fraction. That's the selling point for this. That any number that can be written or rewritten as a fraction is called rational. So why is it that the whole number here is also rational? Because, for example, if I say 5, can you write 5 as a fraction?
Yes.
Yes, you can. Can you write 0 as a fraction?
Yes.
0 over 2, 0 over 4, doesn't matter. 0 divided by 4 is still 0, right? So you can still write it as a fraction. And I said terminating decimal. We just got that case. 1.5, we convert it back to 3 over 2, which is a fraction. Repeating, you gave me 0.33, which is 1/3. It's also a fraction. So notice that any number that can be written as a fraction is called rational. But let me answer this question. Is any rational number can be a whole?
No.
No, because if it's a decimal, it won't probably be a whole, right? See it? So 2.3, even though it can be converted back as a fraction, but is it a whole number?
No.
No. So it's not working like that. Okay. So be very careful when you classify your number, and we'll take a look at it in a minute. So the last set here that I want to introduce to you, which is a set of its own, over here on the side, is called irrational. And this side right here is what we call the null fraction zone. Can't write it as a fraction. And I classified that last decimal type. What is that called again? What's that last decimal type? Non-repeating and non-terminating. And we have a good example for that. Pi is definitely a good example of that one. Okay? Any questions so far in our number system? Different types, different names, different categories, and you have to remember where does it belong. Okay? So now that we have a good understanding of the basic foundation of the number system, let's take a look at this one. I have rational on the left-hand side, and I have irrational. I want you to tell me if it's rational or irrational. Here's the first one. Rational or irrational? Yes?
Rational.
Rational. Very good. It is rational. Okay, no. Let's try it again. Okay, whatever. Let's restore it. Okay, it is rational. Very good. It is rational, so it goes on this side. What is it also known as, besides rational? What else do you call this too? It's also a whole. It's also a integers. It's also a natural. And
Whole number.
it's also a real number, isn't it?
Yes.
There it is. Automatic. Oh, is that good? What about this one? I don't know. There it is. Square root of 8.
Rational.
Rational or irrational?
Rational.
Why rational? You tell me that you can actually convert that back to a fraction.
Let's see.
Can you?
No.
Can you write this as a fraction?
No.
No. So because of that, it's on this side. So notice that it's a square root, but it's on the irrational side. But look at this next square root number. Tell me, rational or irrational?
Rational. No. Rational. Rational.
Who thinks it's irrational or rational?
I don't think it's irrational.
Okay, why is it rational?
Because it's 2.
Thank you very much. So sometimes the square root can be rational, and it also can be irrational. Because notice here, the square root of 4 is 2. And you know that 2 can be written as a fraction. That's why it's on the rational side. Does that make sense?
Yes.
Okay, any questions on how to do that? Okay. No, it's not both.
But I thought irrational was like.
Think. Irrational, you can't write it as a fraction, right? irrational. No fraction zone? This is fraction zone? The square root of 4 can be written as 2, isn't it? The square root of 4 is 2. So the square root of 2 is, square root of 4 is 2. Isn't 2 2 over 1? Is that a fraction? Because you said, yes, I can write it as a fraction, therefore it's automatically on the rational side. Yes?
So it's a rational square. The square root is rational if it's a perfect square.
Good. If any perfect square number is automatically rational. Any number that's not a perfect square is automatically irrational. Does that make sense? Okay, so hold on here. Now the next thing I want to discuss with you is called closure property. I want to have to squeeze this in, otherwise I will forget. What does it mean though? Well, what it means about closure property is that when you start with one type of number, it has to end with that same type of number. Well, what am I talking about? For instance, I give you 2 integers, okay? And then I ask you to go ahead and add them together. Okay, so here are all my 2 integers, 2 and 4. If you take these 2 integers, these are integers, right? Notice I'm using I for integers. If you take 2 plus 4, what do you get back?
6.
6. What is 6? What type of number is 6?
It's real rational.
Well, we know it's real, but notice, is 6 still an integer?
Yes.
You see it? Mainly, does it have that integer still in its integer category? Because it is, notice that if I start with integers and I end with integers, this is what we call a close, because it stays the same throughout. It doesn't change. So in a case where we have something like this, watch what happens. Same thing again. I have 2 integers again, 2 integers, 2 and 4, and this time I ask you to divide. If you take 2 divided by 4, 2 is an integers, right? 4 is an integers, but if you take 2 divided by 4, what do you get back?
2.
Oh, whoa.
5.
2 divided by 4 is
0.5.
0.5, or 1/2, correct? Is that true?
Yes.
But what do we call this number to be? What type of number is this? Fraction is called what? Rational. Oh, watch what happened. Integers, but I end with fraction. Not the same. It's not closed. We call this an open case. Okay, and the first case right here is a closed case. That's the main difference. Closed means everything has to stay the same from start to finish. If it's not, that means you start with one type of number and you end with a different type. That's open case. It's not following the closure property. Yes.
Like this, how come it can be rational? Like 2 and 4, is that rational?
No. Okay, it is rational, right? However, for this particular problem, I specifically specify that these are integers. I specified ahead of time that I give you 2 integers. I expect to get back an integer, right? If it's going to satisfy the closure property. If it's not, then you just say it's not. This doesn't stay closed. Okay, is that clear on closure property? It's pretty short. Okay. Next one right here. I want you to look at this. Hopefully you can actually answer for me. There we go. Thinking. What?
I know it all.
What's special about each of the square root number? What do you notice? Yes? What do we call them? I know it's square root, but what's so special about each number that you see? What's so special about that? Yes?
It goes in order.
Well, it is in order, but what's so special about each and every single number? Yes? Well, of course they're, okay. Notice you said rational and not irrational, and she's right. Why are these all rational?
They're not terminating.
But what do you notice about each one? Yes. Thank you so much. Say that loudly. Say that loudly.
They're perfect squares.
They're perfect square numbers. Thank you very much. How do I know a perfect square? Because a perfect square is formed by taking a number, whole number, times it by itself. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10.
That's what I meant by it.
See that? That's how you remember. If anyone ever asks you, give me a perfect square number, just think of a whole number, multiply by itself. That's how you get a perfect square number. And so what's so unique about it? Because if it's a perfect square number, you can always take the square root of it. Then what is the square root of 1? 1. Square root of 2, 4? 2. 3, 4.
5, 6, 7, 8, 9, 10, 12.
Okay, so you understand that part, right? Right? It's pretty easy to understand. So now that you've seen the pattern, I want you to look at this next set of numbers. What if I want to take the square root of a fraction? However, notice what do you look when you look at this fraction right here? What's the first thing you recognize?
49.
Improper.
I see the.
Okay, first you recognize 49 as perfect square number. What about 121? Is that a perfect square number?
Yeah.
So when you recognize the fraction that has numerator and denominator as perfect square numbers, you can always break your square root into 2 parts. There's the numerator, there's your denominator, and then you take the square root separately. 11 over?
7.
That's how you deal with it. Is that good?
Yes.
Okay, check this one out, see if you can actually do this. I'm trying to give you a bigger number here. What is that going to become?
9 over
15. Can we reduce that?
Yeah. 3 over 5.
Good job. There you go.
No, bro.
Question so far? So, easy, right?
Yes.
What about this one? I hope you still recognize this. Not trying to be tricky or anything, but what about this? Listen.
1.1.
How do you get that answer?
Decimal.
Okay, what's the, okay, how do you come up with 1, 1? What do you see up here?
121.
Oh, thank you very much. No, she dropped the decimal. 121 and 11 times 11 is 121, right? But I showed you this before, that can we actually take that decimal number right there and convert it back to a fraction? The last value of this is 100, right? So therefore we write 121 over 100. See that? So if it's 121 over 100, we can now take the square root of it, which is 11 over 10, and we divide it 1.1. That's how we deal with decimal values. So always, if it looks complicated to you, convert the decimal back into your improper fraction, or and then try to do it that way. We're good with that so far?
Yeah.
Okay, good. Okay, so like I said, the last thing I wanted to teach you is to take an estimation of a square root of a number. We all know what the square root of 4 is. It's 2. The square root of 16 is 4. Easy, right? But what if I asked you to take the square root of 8? Then you're like, wait a minute. Is 8 a perfect square number? No, it's not. Because you cannot find a whole number multiplied by itself to get back to 8. However, if I ask you to estimate that number, well, guess what? We can. All that you have to do is find 2 perfect square numbers. One right after the 8 and one right before the 8.
2 and 3.
Perfect square number.
9.
4 and 9. You see it? I know you said 2 and 3, but that's not the perfect square number yet. You have to square it first. See it? That's the main difference. Perfect square number, you have to take a number, square it. Okay, so 4 and 9. So 8 is in between 4 and 9. So the next thing is you actually expand everything. You start counting. 4, 5, 6, 7, 8, 9. You see that? And watch what happened. The square root of 4 is 2. The square root of 9 is 3. And since we have 6 numbers here, and we split it halfway, this halfway mark is 2.5. Do we agree?
Yes.
And since 8 is on this right-hand side of 2.5, it has to be bigger than 2.5. So can we safely estimate it about 2.7?
Yeah.
So there we have it. So the square root of 8 is approximately 2.7. That's how we estimate it. Yes? Where did I get the 0.5? Look. Okay, look. 2 and 3, halfway of 2.3 is 2.5. Makes sense? Okay, try another one. What if I ask you to take the square root of 17? So what's the first step here? What would you have to find? 2 perfect square numbers. Very good. 16 and 25. This is 4 times 4, so immediately right after the 4 is the 5, so 5 times 5 is 25. Then you start expanding. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and now I have 2, 4, 6, 8, 10, right? I split halfway, so 5, 5 on each side. Agree?
Yes.
This is 4, this is 5, so the halfway mark between 4 and 5 is 4.5, and so since the 17 is right here, closest to 4, so can we safely estimate about 4.1, 4.2?
Yes.
So it's still good, right? There it is. And that's how we estimate our square root number.
I get it.
Okay, question on that? Okay, now you have a good idea. I'm going to go give you a whole bunch of numbers.
No.
Okay. Notice I have this set of numbers out of order. What if I want you to rearrange this set of numbers? What's the best method to rearrange numbers? Do you know?
Least to greatest.
Okay, well, I was definitely specified. I want you to arrange this set from least to greatest. But what's the best way to order these numbers? Yes. That's one way to do it, right? But to get to that point, how do we organize them? Yes.
Make them like all into like one part.
What? Okay, so you're basically trying to convert everything to one type of number, right?
Yeah.
Okay, but that's going to take a while. But what I'm saying here, yes. Okay. But my suggestion, if you listen to me, is start with a number line.
Oh yeah.
Like this. First, start with the first one. 2/3. 2/3 is in between what two numbers? 1 and 0. So right here, here's my 1. And since it's 2/3, I have to divide this part into how many sections? 3 sections. And I need 2 parts of that, right? So there it is. I just put on 2/3. How hard is that? And I'm done with that one. I move on to this next one. It's a negative, so I know it's on the left-hand side of 0, right? But we just learned how to estimate the square root. What is the square root of 5?
2.
Approximately.
215.
4.9.
Square root of 5 is pretty close to the square root of 4, right?
2.
About 2.1?
Yeah.
Fair enough? Isn't square root of 5 very close to the square root of 4? And we know that square root of 4 is 2.
Yes.
So we can say about 2.1. Negative 2.1, so this is negative 1, negative 2, so we can just put it right here and call this the square root, a negative square root of 5. Negative 2 is also right here, right? Here's negative 2. 1.7. So I'm just going to have to, this is 1.5, so 1.7 is around right there. And of course, what is the square root of 7? What is it closest to?
4.9.
Well, think about it. Here's a 4, 5, 6, 7, 8, 9, halfway point. So this is 2 and 3, 2.5, pretty close to 2.5, bigger than 2.5, so 2.6. Okay, so 2.6. So this is 2, this is 3, 2.6 is around here somewhere. So this is square root of 7. There, guess what? I just have my number sorted. Done. If you read it this way, this is from the least to greatest. If you read it backwards, you have from the greatest to the least. It's done. It's already sorted. So the strategy is here is if you put it on a number line, you're good to go. Yes.
Wouldn't it be easier just doing least to greatest by itself?
What happened?
Wouldn't it be just easier doing it least to greatest, just like writing it? Or no?
But notice that as you put your point on the number line, it's automatically sorted. See it? It's automatically sorted. Okay? It's a strategy, guys. I mean, I'm just, you might have a different way to do it, but this is a good way to do it. Okay? Any questions so far on how to work this out? We're good? Okay.